Good afternoon, everybody. Welcome to this afternoon session. Before we begin, I would like to make an announcement about some changes in the program. That due to some delay in the arrival of Stefano Facchini, his talk will be presented tomorrow. And so the current session will start with Tomoyuki Yamakami from Japan, and then after that we will have the other two talk by Andrzej Lima and Özlem Salih. So let me give the floor to Tomo from Fukui, Japan.
Okay, well, thank you very much for introduction. Sorry for the change of the the schedule. Well, first I had to excuse myself because I was supposed to make a changes tonight because my talk is scheduled tomorrow, right? At the same time. So I just quickly made a modification, and also tonight didn't make any rehearsal. So well, even if my talk is so awful, but then don't complain, okay? All right. Okay, so well, this is just the outline of my talk. So this is the talk all about topological spaces and continuous maps. Those are mathematical concepts. And also I'm going to talk about the topological automata, right? In particular, I'm going to introduce the model called one-way deterministic topological automata. Well, the shorthand is 1DTA, deterministic topological automata, right? And through this talk, I'm going to explain about the fundamental properties of this particular machine model, and also explore some effects of the topological features using this 1DTA. So that's the main purpose of this talk. Okay, so I start with the very basic definition of the topology. So this is just the brief history about the topological automata. Well, that started with the 1970s. As far as I know, this might be the oldest, but then maybe you're wrong, right? Well, the Blower first discussed the transducers. So that is slightly different from, because I'm going to talk about acceptors or recognizers, okay? And then later in the 1970s, Ehrlich and Kuhnel, probably my pronunciation is not right, but they continue talking about transducers using this, the notion of the topology. And year 2000s, the Giandel, he introduced another model, using the acceptors for this topological automata. So my work today is more or less based on Giandel's idea, but then I just give them slightly different definitions. So you will see what the definition would be, right? So I start with the very basic notion of topology. So particularly I'm interested, we are actually talking about the general topology. There are several different kinds of topology, but another word for this general topology is the point set topology. So everything is actually based on the points. So that assuming that so we have a set of points, right? And the topology refer to the axiomatic collection of the subset of the points set. And we have one element of this T sub V, the topology is called an open set. The complement of an open set is called a closed set. So there are sets that are both open and closed. Those sets are called a clopen set, or just a shorthand for the open and closed. Right? So the neighborhood is another term for an open set. So I interchangeably use in the neighborhood and open set. Right? The topological space is basically the point set and this topology. Right? But sometimes I just simply write V instead of the V, a pair of the V and T sub V. Okay. So I'll just give you the typical topological spacing. The trivial topology is the well, there's only two open sets. The empty set and entire set. And discrete topology, so that is the actually the extreme opposite of the trivial topology. That all possible subsets of V are actually open sets, right? So this is the most powerful topology. And the finite topology refers to the the open set. That set of open sets is just a finite set. Okay. One example is something like this one. There are 4 points here, and a circle refers to the open set, right? So that's the total open set here. The open set is actually written here. The closed set is just a complement of those open sets. That means we have those kind of things, right? The open sets, well, if you just compare the open set and closed set, and you actually find that empty set and the entire set, and those are the only open sets in this topological space. Okay, so I go with the definition of the continuous map. So the map is called continuous if for any point and any neighborhood. So I just to give it here. So take any possible neighborhood of this particular point here, right? So we can always find an n prime. So that is the open set that mapped inside this n. Right? So this is the definition of the continuous map. Okay, so well, then I have to introduce some more definitions here. Well, the notion called the topological moment. So this is just the extension of the standard monoid. The monoid is the well, here the V is as before it's in the topological space, and this notation. Well, okay, so this handwritten letter B is the set of an operator. So this particular notation refers to the set of all continuous maps defined on this V. But the maps have to belong to B. So that's the subscript B stands for, right? And supposing we have the binary operator and this pair, right? The set and an operator. This is called a monoid that satisfies the two axioms, right? So we just change the order of the application of this particular operator, and I is the identity, work as an identity. Now the V and another operator is a black dot is called the left act over this set of operators with this white circle means that the V is the entire set, entire space, right? This satisfies two axioms. So this is actually the white circle and the black circle, right? The V is the element. B1 and the B2 are operators. So we can actually change the order of the application of the black one. And another one is the identity here. So that the I does not change the element of B. So if the two axioms are satisfied, then we call it left act. Now we will come to the the point of the defining the topological monoid. This pair is called the topological monoid if the this itself is a monoid and satisfied in the two conditions. This white circle, the operator, is a continuous map, and also the V and this black one, the black dot, is the left act. So in this case, this pair is called topological monoid. Okay. Now we are going to introduce the most important notion called an automata base. So this is the basis for the rest of the talk. Okay. V and B and O, those triplet is called an automata base. If this V is the set of the topological spaces, we call it the configuration spaces. you know, if you hear the configuration space, you actually have some idea what's going on here. I'm going to give a more precise definition later on. And B is a set of a continuous map from V to V. The V is the element of this handwritten letter V. And O is a set of observable pairs. The pairs like this one, E accept and E reject. Well, so this E accept is called an accepting space, and E reject is the rejecting space. And those two sets must be token sets. So that's the important requirement for the observable pair. Now we'll define the 1DTA, one-way deterministic topological automata, for shorthand for the 1DTA. Right? We fix the automata base. The automata base is defined in this way. Right? So we have three elements, V, D, and O. So based on this, we fix this triplet, and we'll consider the automata based on that one. Right? So the 1DDA have this form, pretty much similar to the standard one. We have the alphabet and end markers and entire the configuration space and operators, depending on associated with each letter. The letter means the alphabet and the end markers. And we have the initial configuration here, and two sets. It's accepting set space and the rejecting space. And we assume that the two sets are do not have the common element. Oh, sorry. Oh, yeah, that's right. This is right. Okay. Now I'm going to explain the configurations and the computation. So we have a definition of the 1DTA. Now then I have to specify how it works. Okay, so we start with the automata base, right? And then we consider the 1DTA defined based on this automata base. So that's M, right? Now the our input is this point, including the both end markers. So the x0 corresponds to the cent mark, the left end marker, and x sub n plus 1 corresponds to the dollar sign, the right end marker. So now this particular machine works in the following way. So this is the entire space V, and we have observable pair, the accepting space and the rejecting space. Now we start with the V0, the initial configuration. We apply B based on, well, I should have put the subscript. The first one is x0. So we apply the B based on an x0. Then we get the first the configuration, and then we apply another B based on the x1, and so on. Eventually, we actually hit the either this set or this set. Then the computation starts. Or we actually read the entire symbols. Then we actually require that the machine has to fall into either this or this by the time of the reading the right end mark. Right? So this tuple, the starting with the V0 up to the V sub m, so this is called the computation of m on this x. So as you see, I'm not requiring the machine to read the whole entire thing. As long as they actually fall into the accepting states or accepting configuration or rejecting configuration, the computation starts. Well, later on, you can actually easily modify the definition so that so you can actually go into the either accepting configuration or rejecting configuration. Exactly, so you are reading the right end. So you can postpone the holding time. But the definition is something like that one. Right? So the important fact is that the conventional finite automata, pretty much all of them, are actually one DTA, topological automata. For example, one-way deterministic finite automata, or probabilistic one, or even a quantum one, or even the push-down automata. Well, all the machines are actually described in terms of topological automata. So this is just one example here, right? So every deterministic finite automata, standard deterministic finite automata, is actually the one DTA. If we carefully choose the V and the B and the O, for example, the V is the collection of the finite set, and B is the the set of the operators, and O is the A or the complement of A, corresponding to the set of K, well, bracket K, right? So in the same way, in a similar way, you can actually characterize those machineries in terms of the topological automata. So that's the beauty of the topological automata. You can actually describe a whole bunch of the finite automata, even in the quantum. Okay. Now I'm going to explain about the basic property of this the new machine model. So first of all, we can actually eliminate in a certain condition. Under the certain condition, we can eliminate the end markers. End marker, the use of the end marker is not really necessary, right? So the operator is called continuously invertible. If and only if every operator that belongs to this the set B is invertible, and also its inverse, say B to the minus 1, is also continuous. Right? So in that case, for every DTA, right, we can actually define another DTA without any end marker. Well, in this case, left end marker, right? Both machines actually have their computational equivalence. That means they actually recognize exact the same language. Well, similarly, we can get rid of the right end marker. So now I'm going to explain the power of the particular topologies. So first, we have seen it in 3 different kinds of topologies. The first one is in a discrete topology. That means every subset of V is open set, right? So this is the most powerful open set. For example, I just draw the basis open set. So if you have the point, then point itself is the open set, and also you can combine the union finite intersection of the open set and the infinite or finite union of open sets are actually open sets. So that's a definition of the topology. But then if you have the topology like this one here, so those circles refer to the open set. So we have 1, 2, 3, 4 open sets. Well, include plus 1. So that's the empty set is also an open set. So in that case, so we can prove something like this one, right? So we can actually take the reasonable automata base with the following property. Well, first we use a discrete topology like this one here, and for each V element, well, the configuration space, for any language, we can actually find one DTA that recognizes L. So that means that any possible language can be recognized by the one DTA using particular treatment. Right? So this is the power of the automata, topological automata. So that we can actually describe everything. Right? Just a matter of how to choose those things. So next one is the trivial topology. So this is the weakest topology, right? The open sets are the empty set or the entire set space. That's it, right? Something like this one here. The trivial topologies like this one. There is no basically circle. Yeah. But then if you have a circle, just a single circle, then this is not a trivial topology. Okay, so for trivial topology, what we can say, so it's very simple. So if you take one DTA using this topology, right? Now we use an alphabet, sigma. So this DTA recognizes only the empty set or the entire sigma star. That's it. Right? Nothing else. So well, the third one is the finite topology. One of the examples is the trivial topology. This is a finite topology. I just remind you that finite topology means that the set of open set, well, the topology itself is a finite set. So we only have the finite number of the open sets, right? For finite topology, one DTA recognizes only regular languages. It's very well. One example we have seen this in one example, right? Okay, now we have to compare the strength of the topology in terms of one DTA. So that's the main purpose of this the research. So first of all, we have to discuss the topologies and the machines, right? The machine is based on the configuration space, but if you look at all the configurations, right? You can define the configurations in an arbitrary way, but we start with the V0 and then move into another configurations. Some configuration may not be reachable, right? But if you consider the whole entire space and the whole entire topology, is it really reflecting the nature of the machine? Maybe not, right? So we just get rid of those points. They are not reachable from this V0. We simply get rid of those things. Then we focus on the configuration space. That consists of the points that are reachable from V0. Right? So this is the definition of the slender DTA. That means V, so entire configuration space, contains no point that cannot be reachable by this machine. So if you just focus on this reachable configurations, and then consider the topology on this, so this reflects the behavior of the machine more precisely than you're actually talking about topology on all points here. So from now on, we actually focus on the slender type DTA. Okay, so supposing we have the properties, whatever it is, we have property, right, and on the point set, and we actually focus on the slender one DTA. Okay, now two property, corresponding to the topology, right? P2 property P2 and the property P1, and okay. Well, before that, I have to introduce the notion here, the means. So fixed and automata base, right, is the triplet. So we say that this triplet meets property P if and only if every slender one DTA. So now then we actually restrict our interest only on DTA. Right? So this DTA satisfies P. So we don't care about non-slender one DTA, only focusing on the slender one DTA. Okay. The property P2 is at least as computationally strong as P1. Now we are comparing the properties, right? Using the computational aspect from the computational aspect. So this means that, well, we consider all possible automata base that means P1. The P1 is here, right? So we can find another automata base here. So that meets P2 here, right? That satisfies the following condition. if you take any possible slender 1 DTA corresponding to the first automata base, we can always find another 1 DTA based on the second automata base. They are actually computationally equivalent. They recognize exactly the same languages. Right? So in that case, so we just write down like this one. The P1 is at least as strong as P2 computationally. But then if you have the same condition, but the inverse, well, the converse of the same condition doesn't hold. In that case, we say P2 is computationally stronger than P1 because there is no other way around. Okay, so we just make the comparison between the two different properties. So I come up with the I just checked out the topology and the topological properties, and so this is one of them. Kolmogorov separation axiom. That means for any pair of the distinct points, topologically distinguished. Topologically distinguishable means that the open set can differentiate 2 points. Like we have an open set that contains x but not y, or y is contained in n but then x is not. Sort of an open set. You have a 2 points, right? You can draw the circle, not including one but not the others, right? So that means open set actually distinguishes 2 points, right? So every 2 distinct points can be topologically distinguishable. So that particular topological space is called is said to satisfy the Kolmogorov condition. Right? The Kolmogorov space is the space that satisfies this condition. Well, we can think about a much weaker condition. So this condition, well, property is actually stronger than the trivial topology. So the theorem says there exists in a topology that not satisfying the Kolmogorov condition, but V is computationally stronger than the trivial topology. So the trivial topology is the weakest, and then so we can find somewhat in the middle of the weakest and the strongest topologies. This is just one. Well, I try to kind of think of the characterize all possible known topologies in terms of like the stronger, the notion of the stronger. But I didn't have much time so far, so it's just the future open question. Okay, so the another thing is that we can actually completely characterize the regular languages in terms of the topology. Well, I omit the whole definition that's come up in this the yellow box, but you can take a look at the proceedings, right? So the regular language is completely characterized automata base that satisfies the ABC 3 conditions. Every element is the uniformization, uniformizable, so sort of the uniform notion. We can introduce a uniform notion, and so this pair is actually compact. That's a mathematical notion, and that means the points are actually covered by the many open sets. Then you can actually pick up the finite numbers and open sets that covers the whole entire space, right? So that's the compactness. And also we have the uniformly topologically equicontinuous. So this is the notion slightly weaker than the standard and continuous notion. And so this L, the language, regular language, is recognized by 1 DTA. So this is actually if and only if condition. So the regular language is completely characterized this way. Right? So it would be nice if you actually tend to give the the same kind of characterization. For example, if you think about it in a CFL, in a context-free language, or all those exotic the language family that all of you actually defined through the conference. Okay. Now the final part of this my talk is about the non-determinism. So first we have defined the deterministic term, right? So we just modified it so that we can actually talk about the non-determinism, right? So to define the non-deterministic machinery, we'll introduce the we'll just extend the standard operation into the multi-valued operation. So this is actually very simple, right? So we take one point here, then we actually take the several points as a set, right? So this operator is called continuous if the B of x is an open set of B2 for any x. So that the image is, well, this is the multi-valued operator, so that the image of this x is also the set, right? So this has to be open set. Okay, so sorry, I have to put there the base here, the extended automata base. So this is the extension of the deterministic automata base. So this is the triplet, similar to the deterministic case, but this B consists of continuous multi-valued operators instead of just a single-valued operator. So that's the only difference, right? Okay, so the non-deterministic machine, so one NTA, non-deterministic topological automata, so that is defined in the following way. The only difference between this one and the deterministic one is the transition operator. That has to be the multi-valued operator. And also slightly different for the acceptance and rejection. So this works like this one, right? We take the standard input x and we apply these operators, the multi-valued operators. And then we actually look at the elements that actually fall into the either accepting or rejecting configuration. Then it stops. So machine accepts the input x if the final element, the configuration, final configuration going to the accepting configuration and m is set to reject x if the final configuration going to a rejection configuration. So here we'll take the okay. So for any extended automata base, we can actually properly take automata base. This is a deterministic one with some particular topology called Dietrich's topology. I just omit the definition. This is a little bit complex. Then one MTA, the non-deterministic topological automata, can be modified into an equivalent, one deterministic topological automata. So that means this is similar to the non-deterministic, the finite automata can be transformed into the deterministic finite automata. And the cost of extending the operator and the space. Okay, and that's all. Thank you for listening, and I'm really happy to take your questions.
Are there any questions? I had a question. During your talk, you mentioned that regular languages you can characterize, and it would be nice to have some others. Do you have any idea how to do this, for example, for context or other?
Well, so first, I haven't considered the characterization. That's just the future work. But it seems to be a here, even if it's in a regular language, the characterization of the regular language, and I have to introduce a whole bunch of topological notions, right? And probably if you look at the context B or much more different language classes. Maybe I had to really, play with all those topological notions. That doesn't seem to be really kind of a nice somehow. So I prefer a much more simpler and intuitive that kind of the concept to characterize those language families.
Okay, so thanks again.
Well, thank you very much.
And for those of you who came,
Sorry. No, that's fine. Well, there's so many ants and flying is around my head actually.
Okay.
Yeah.
So,
Oh my gosh. Wow.
Okay, I can take picture of you.
Oh,
can we take two together?
sure.